To test a theory, my twin brother and I conducted an experiment at age 12. My older brother, by 3 minutes, volunteered to fly into space at close to light speed. After about a little more than 5 years, he came back to Earth. He looks exactly the same as he left Earth.
So how did this happen? Why do I still look the same? First, let's investigate the complicities of light and the importance of the observer.
If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here.
Okay, now I know how complex this is, but I still don't know why I'm the same after 5 years passed on Earth.
Let's see how the observer can change everything.
Oh, but constant motion feels just like sitting still.
And if you want to know what it feels like to move at 1,000 miles per hour, just look around. Because of the Earth's spin, we zip along our time zone at a speedy 1,000 miles per hour. And because of its motion around the sun, the Earth carries us through space about 67,000 miles per hour. And because of the motion of our solar system, about the center of our galaxy, we are moving at more than 500,000 miles an hour. But it's not enough to ask, how fast am I moving? We must ask, how fast am I moving relative to some other thing? We begin at a moving walkway at the airport. The walkway is moving at a brisk 3 miles per hour. So, if Susan simply stands on the walkway, she is moving at 3 miles per hour, relative to Sarah, who is standing still but not on the walkway. If Susan walks on the walkway at 3 miles per hour, she can accurately say she is walking at 3 miles per hour. But Sarah sees her moving at 6 miles per hour. And if Susan walks against the walkway at 3 miles per hour, Susan can still say she's walking at 3 miles per hour. But now Sarah sees her as standing still, 0 miles per hour. So our first conclusion is that two observers can simply add or subtract their speed with respect to each other to any measurement of velocity they make. This idea is the basis of classical relativity.
I'm understanding now.
Sure you do. Well, now let's see why time changes as you move in space and I stay on Earth.
Here's a graph of a car traveling due east at its maximum speed of 100 miles per hour. It is making no progress in the northward direction. All of its speed is going east. Now let's turn a little to the northeast. Even though the car is still doing 100 miles per hour, it is going less than 100 miles per hour in the east direction, because some of the speed is being used to go north as well. Space and time can be thought of in the same way. Everything in the universe is traveling through space and time at the speed of light, the maximum speed available. Picture time replacing east and space replacing north in the car example. If you are sitting still in space, not going north, you are traveling at the maximum speed through time, east. But if you start moving in space, north, your progress through time will slow down, since some of your speed has been diverted. The faster you go through space, the slower your progress through time. If you could travel at the speed of light in the space direction, you would make no progress in the time direction at all. Time would stand still, as it does for a beam of light. And if you could go faster than the speed of light, you could travel backwards in time. Let's imagine constructing a clock in which a beam of light bounces between two mirrors. Whenever the light strikes the bottom plate, the clock advances. The advantage of using this kind of clock is that we can be sure that the observer who looks at the clock will see the timing mechanism, the beam of light, moving at the same speed. If two such clocks are stationary, then we would expect the time indicated on each clock to be precisely the same. But what happens when one clock is in motion? Notice although both clocks are identical, the moving clock ticks slower than the one at rest. In order to understand why, notice the paths of the light beams. The light in the stationary clock travels up and down vertically, but the light beam in the moving clock must travel a longer diagonal path. Since both beams travel at the same speed, and the upper beam travels a longer distance, the stationary observer sees the moving clock run slower than his own. This slowing down of clocks in motion is known as time dilation. It should be stressed that a person moving along with the moving clock would notice nothing unusual at all. The clock and the flow of time would seem to progress normally. According to this observer, he is at rest and the other observer is moving past him. According to him, it is the other clock that is running slowly. The flow of time in Einstein's universe is entirely relative. These unusual effects of relativity, time dilation, and length contraction depend dramatically on your velocity. At everyday speeds, they are simply not noticeable. The fastest that humans have ever traveled is a few miles per second, a tiny, tiny fraction of the speed of which light travels, 186,000 miles per second. But in Einstein's universe, space and time are no longer absolute. There is no single time that exists for everyone in the universe, no distance in space that everyone can agree on. Space and time, like classical velocities, are only relative.